The goal of this lesson is to prove Sylow's first theorem, which was proved by a Norwegian high school teacher in 1872. This is one of the most important theorems in finite group theory, and you can think of it as a partial converse of Lagrange's theorem. Recall that Lagrange's theorem states that given a finite group G, any subgroup H of G will have an order that divides the order of the group G. But the converse is not true. So given a finite group G, and a divisor D of the order of G, there does not necessarily have to be a subgroup with order D. So to illustrate the fact that the converse of Lagrange's theorem is not true, let's look at the alternating group A4. So for example, the alternating group A4, recall that A4 consists of the even permutations of S4. So the alternating group A4 has order 12. And it's actually a fact that A4 is simple, which means it has no normal subgroups other than the identity group and the group A4 itself. So the alternating group A4 has no subgroup of order 6, which would be normal because it would have index 2. But A4 has no subgroup of order 6, which is a divisor of 12. So now I'll state Sylow's first theorem, but it's going to be a while until we actually give the proof of this theorem. But we're going to look at the theorem and discuss what it means before going through the process of proving it. Sylow's first theorem says that let P be a prime and let G be a finite group then if a prime power of P, so if P to the power K divides the order of G, then it is true that G has a subgroup of order P to the K. So again, this is a partial converse of Lagrange's theorem. If we have a prime power divisor of the order of a group, then it is true that G has a subgroup of that order. But as the counterexample above shows, 6 is not a prime power, and that's why it's possible for A4 to have no subgroup of order 6, and that doesn't contradict Sylow's first theorem. So let's look at another example to illustrate what Sylow's first theorem is telling us. So imagine you have a group G with order 360. So if all we know is the order of the group, then let's see what Sylow's first theorem tells us. Well, 360 is 8 times 9 times 5, so I can write this as 2 cubed times 3 squared times 5, and therefore Sylow's first theorem says that G has at least one subgroup of each of the following orders. Two, 4, 8, 3, 9, and 5. So these are all the prime powers dividing 360. So there are some limitations, right? This doesn't say anything about subgroups of order 6 or order 10 when you take a factor of 360 that's not a prime power. But it is still a powerful theorem, and we know at least that there are these subgroups of this group G. Another example of the usefulness of Sylow's first theorem is the proof of the next result. So this result is due to Cauchy, which was proved in 1845, and it took Cauchy about 9 pages to prove the following result. But if we can for a moment assume that Sylow's first theorem is correct, we can actually prove Cauchy's theorem quite quickly. So let G be a finite group. And let P be a prime dividing the order of G. Then Cauchy's theorem states that G has an element of order P. So again, we're going to prove this by assuming that Sylow's first theorem is correct. So by Sylow's theorem, Sylow's first theorem, we know that G has a subgroup H of order P. But H is a subgroup of prime order, and therefore H is cyclic. So since H has prime order, H must be cyclic. So then we can write H as the cyclic group generated by some element X for some element X in H. But then the order of X equals the order of the cyclic subgroup generated by X, and that is equal to P. So X is the element of order P. So again, Sylow's first theorem is very useful, and gives us a quick proof of Cauchy's theorem. So we now need to present some tools that will be used to prove Sylow's first theorem. When we prove Lagrange's theorem, we actually proved it by partitioning the elements of a group into cosets. We will actually prove Sylow's first theorem by partitioning a group into something called conjugacy classes. So let's discuss conjugacy classes. First, we define conjugate elements. So two elements, A and B, of a group G are called conjugate if there exists an element G in G such that G A G inverse equals B. So recall that G A G inverse is called the conjugate of A by G. And so we see that if the conjugate of A equals B, then A and B are called conjugate elements. Now for a given element A, if we put all the conjugates of A into a set, this is called the conjugacy class of A. We're going to denote this by CL of A. So this represents the conjugacy class of A. And this is the set of all conjugates of A. Okay, so the conjugacy class of A is a set of all elements of the form G A G inverse, where G is any element of the group G. So it's actually true that the conjugacy classes of the elements of G actually partition the group G. So this is going to be useful when we prove Sylow's first theorem. So let's look at some examples of conjugacy classes. So the first example, consider the conjugacy class of the identity element. Well, if you take any element G in the group and take the conjugate of the identity with G, then this just equals the identity, because G times 1 is G, and G times G inverse is the identity. So the conjugate of 1 by G is equal to 1 for any element G in the group. So we see that the conjugacy class of the identity element is always just going to equal the set containing the identity element. So the conjugacy class of the identity element is the set containing only the identity element. So this is true for every group. Second example, now consider a group G that is abelian. So if G is abelian, then we can commute elements. So G inverse would be equal to G inverse A, which would just reduce to A for any element G and G. So we see the conjugate of A, again, is just the set containing A. And this is the conjugate class for any element A in G. So if G is an abelian group, then all the conjugacy classes contain exactly one element. Third example, so a little bit more generally, consider A in the center of G. So recall, the center of G is the set of elements that commute with all other elements in the group G. Well, if A commutes with every element of the set G, then the conjugacy class of A would again just be the set containing A. So A is in the center of G if and only if the conjugacy class of A is the set containing only A. So to work this out in more detail, if A is in the center of G, that's true if and only if GA equals AG for all G in the group. This is true if and only if G inverse equals A. So again, just multiply both sides of this equation on the right by G inverse. So we see that G inverse equals A for all G in the group. And this is true if and only if the conjugacy class of A contains only the element A. So we see that A is in the center of G if and only if the conjugacy class of A contains only the element A. Now let's look at a more specific example. Consider the group S3. We can check that the conjugacy classes for S3 are the set containing only the identity, the set containing all transpositions, so 1, 2, 1, 3, 2, 3, and the set containing the 3 cycles, 1, 2, 3, and 1, 3, 2. So we can just show this by direct calculations of the conjugates. So for example, if I wanted to look at the conjugacy class of the transposition 1, 2, I would look at the conjugates of 1, 2 with every other element. So this would be the set containing 1, 1, 2, 1 inverse, 1, 2, 1, 2, 1, 2 inverse, 1, 3, 1, 2, 1, 3 inverse, 2, 3, 1, 2, 2, 3 inverse, 1, 2, 3, 1, 2, 1, 2, 3 inverse, and the element 1, 3, 2, 1, 2, 1, 3, 2 inverse. And just by simplifying each of these expressions, note that the inverse of the identity is itself, the inverse of any transposition is itself, the inverse of a 3-cycle, you just write the 3-cycle backwards. So the inverse of 1, 2, 3 would be the cycle 3, 2, 1. So then just simplifying this, we'll see that we only actually get 3 elements when we simplify this, and it would give us the elements 1, 2, 1, 3, and 2, 3. So you can verify this on your own. And we'll see that if we look at the conjugate class of each element of S3, we would get one of the 3 conjugate classes that are listed here. But again, as I noted earlier, if we look at the conjugacy classes, they actually partition the group S3. Whereas before, when we partitioned by cosets, we saw that each coset had the same exact amount of elements. It's not true for conjugacy classes, but every element is in exactly one conjugacy class. Well, next we'll prove a lemma that will be used in the proof of Sylow's first theorem, but we need to first recall the notion of a centralizer of an element. Recall that the centralizer of an element A in G, denoted by capital C sub G of A. This is the set of all elements in G that commute with A. And we've shown in the past that the centralizer of an element is actually a subgroup of G. So we have that the centralizer of A and G equals the set of elements G and G, such that GA equals AG. So this would be, again, the set of elements that in G that commute with A, but equivalently, this is the set of elements G and G such that the conjugate GAG inverse equals A. So these are equivalent formations of the centralizer of A and G. So let's state the following lemma. We'll call this lemma 1. So lemma 1 states that if A is an element of a finite group G, then the order of the conjugacy class of A equals the index of the centralizer of A and G. So recall that since G is a finite group, this index just equals the order of G divided by the order of the centralizer of A and G. So we see that in particular that the order of the conjugacy class of A is actually a divisor of the order of the group. The order of the conjugacy class of A actually divides the order of the group. So now let's give the proof of this lemma. So to prove this lemma, we're actually going to use a map phi from the set of left cosets of the centralizer of A and G to the conjugacy class of A. So let's define this map. Let's call it phi. And it maps left cosets of the centralizer to conjugates of A. So this goes to the conjugacy class of A. And the way we're going to define this function, we'll define phi of the left coset G will be equal to the conjugate G A G inverse. And we claim that phi is actually a bijection. So to show that phi is onto, well, by the definition of the function, it's onto, because if we have an element of the conjugacy class, so let's let x a x inverse be an element, be a conjugate of A for some element x in G, then we would take phi of the left coset x times the centralizer, and that would equal x a x inverse. So basically, by the definition of the function, it's onto. Now let's show that phi is 1-to-1. So suppose phi of the left coset x times the centralizer equals phi of y times the centralizer. And that tells us that the conjugate x a x inverse would be equal to the conjugate y a y inverse. But by multiplying both sides on the right by y, we see that this implies that x a x inverse y equals ya, and then by multiplying both sides on the left by x inverse, we get that a x inverse y equals x inverse y a. And if we look at this, we see that if we group this, we see that the element x inverse y actually commutes with a. So that tells us that x inverse y is in the centralizer of A. Then by properties of cosets, this tells us that the left coset x times the centralizer has to equal the left coset y times the centralizer. And therefore, we see that phi is 1 to 1. So we have a bijection from the set of left cosets to the conjugacy class of A. So since phi is a bijection, the domain and the codomain have the same size. So we see that the order of the conjugacy class of A would equal the order of the set of left cosets, and the number of left cosets is by definition equal to the index of the centralizer in G. And so that proves the lemma, but we can say that since G is finite, this equals the order of G divided by the order of the centralizer of A. And from this last equation, we see that the order of the conjugacy class of A actually divides the order of G.